So let's start with viscosity. Even if you haven't heard the term viscosity before, you've definitely experienced the phenomenon. The official definition is resistance to flow. In other words, if you pour a substance or if that substance is moving down a hill, how fast or slow will it move? You probably know that if you pour water, you'll have a very different experience than if you try to pour ketchup or honey or something like that. So, what affects viscosity? Basically, intermolecular forces. The stronger the intermolecular forces holding molecules of a substance together, the more it's going to want to hold its shape and not move around. Here's another example of viscosity. Two types of lava on the big island of Hawaii. This lava, what native Hawaiians call pahoehoe, is smooth and runny, while the other lava, called a'a, is chunky and viscous and moves slowly. If you have a pahoehoe flow moving towards your house, get out quick. But if you have an a'a flow heading your way, you may have hours or even days, sometimes weeks, to get to safety. Remembering that viscosity is based on the strength of intermolecular forces, which of these two substances, NH3 or pH3, will be more viscous? So they're both liquids, and they're both going to flow, but one of them is going to be more viscous than the other. So if you're not sure about which is more viscous, start by thinking about the molecular geometry and electronegativity differences, then use that to determine what sort of intermolecular forces you'll have. Here's NH3. There's a large electronegativity difference between nitrogen and hydrogen, so this will have a strong dipole and form hydrogen bonds with itself. pH3 has a similar geometry, but there isn't a large electronegativity difference between phosphorus and hydrogen, so this will only have dipole-dipole forces holding it together. Hydrogen bonds are stronger than dipole-dipole forces, so NH3 will be more viscous. Next up, will C6H14 hexane or C12H26 dodecane be more viscous? Let's pop pictures up on the screen, and you can see that these are both hydrocarbons, all carbon and hydrogen, but since there's no large electronegativity difference between hydrogen and carbon, all we're going to get for both of these are London dispersion forces. The question is, are they going to have the same strength of intermolecular forces? The answer is no. It turns out the larger the molecules you have, the easier it is to get instantaneous dipoles, and therefore the more you're going to get London dispersion forces. So C12H26 dodecane will have stronger London dispersion forces and therefore will be more viscous. Now let's talk about the second physical property that depends on intermolecular forces, which is surface tension. You are probably familiar with this phenomenon because you might see, for example, bugs that float on water. They don't just sink to the bottom. Now, you know that there are hydrogen bonds holding each water molecule to the molecules next to it, but think about how this varies with location. A water molecule in the middle of water has lots of water molecules to connect with, but one on the edges has fewer opportunities. It can't connect to air. It wants to connect with as many water molecules as possible. If you poured water on a table and it lay flat on the table, there would be a lot of molecules exposed to air. So basically, the water is going to reshape itself as much as possible to minimize the surface exposed to air. In an ideal world, surface area is minimized in a sphere. But water doesn't do that here because of gravity. If you go up in space, though, that's exactly how water behaves. Another phenomenon that we see that's related to this is called a meniscus. When you get into lab and look at water in a graduated cylinder, you will see that it makes a curved shape like this. That's because water molecules have three choices. They can try connecting to air, which we already know doesn't work. They can connect to each other, or they can stick to the glass. As it turns out, glass is highly polar, and water would rather stick to it than to itself, so it moves to maximize how many water molecules attach to the glass. Now, by contrast, mercury is a non-polar liquid. It doesn't want to stick to anything polar. So if you were to put it in a graduated cylinder, you'd see that it curves the other way. It doesn't want to be around a polar substance, and so it's going to minimize the amount of mercury that's next to the glass, and that's why we get this upward curve. So the third physical property we're going to talk about is boiling points. Although this sort of stuff is applicable for all phase changes. Basically, the stronger your intermolecular forces, the higher your melting point. The stronger your intermolecular forces, the higher your boiling point. Now we're going to talk about three aspects of how intermolecular forces affect boiling point. First, the type of intermolecular force you have is going to affect the boiling point. Here we have water, which is hydrogen bonds, and methane, which only has London dispersion forces. We'd expect water to have a higher boiling point, and indeed it does. Its boiling point is 100 Celsius as opposed to methane's minus 161 Celsius. So we always consider the type of intermolecular force that is present. Second, consider the molar mass of the molecule. The more atoms a molecule has, and the heavier those atoms are, the more electrons they will have, and therefore the easier it will be to get an instantaneous dipole. So London dispersion forces in particular will be strongest in the heaviest molecules. Here we see hexane, which is much larger than methane, and of course then it has a much higher boiling point. So you always want to keep the molar mass in mind. Finally, let's look at pentane, C5H12. If I asked you to draw a structure for pentane, you'd probably draw something like this. This molecule has a boiling point of 36.2 Celsius. But this molecule is also C5H12. It has the exact same molar mass, and yet its boiling point is lower. Why is that? Well, as you can see, this first molecule is all spread out, while the other one is literally shaped like a ball. I know you can't see that very well in 2 dimensions, but if you build a model, it's true. So it turns out that if you have a lot of surface area, there are greater opportunities to connect with other molecules, and then you end up with stronger intermolecular forces. So there are many physical properties that are related to intermolecular forces, of which I've talked about 3 here. There are others that exist, like we'll talk about vapor pressure in another video. So I hope this was helpful, and I will see you again soon.